Hi, my name is Xiaoyan. I work in the Physical Analytics team led by Hendrik Hammond at the IBM TJ Watson Research Center. Today, I would like to give a brief introduction to IBM Pairs, a geospatial data and analytics platform. Before I get into the technical detail, I would like to share the story of how the idea of Pairs has started in the first place. It's back in 2012 in this vineyard in Central California. A group of IBM scientists and software engineers started a project with a large winery. The idea was to use sensor data in combination with physical models to estimate the day-to-day water usage and water loss, and to prescribe irrigation schedule by taking into account the weather conditions. The goal was to improve water usage efficiency, improve grape yield and uniformity. To determine the individual need for water, they deploy a physical model of energy balance, which considers the heat transmitted from the sun's radiation, the heat loss from the plant, as well as the heat transform between the plant and the ground. Although the physics of such a model is not that complicated, it requires integration of lots of real-world data, such as temperature, solar irradiance, wind, emissivity, surface albedo, soil, and satellite imageries. Coupled with that, they also developed a smart irrigation system that will irrigate individual area on demand. The complex communication network connects hundreds of sensors and valves together and enable precision irrigation remotely via the cloud service. Fast forward to 2015, the project was hugely successful. After running the vineyard for 3 years, they achieved 26% more grape yield, 15% more efficient usage of water, and 50% better grape quality. Fortune Magazine, Harvard Business Review, New York Times have all reported this story. From this engagement, we learned how impactful it can be with a little bit of physics combined with real data from physical world. But here are two more important lessons we learned that have not been publicized very much. First, we learned how important it is to integrate geospatial and temporal data. We have many sensors in the field, such as moisture sensor, temperature sensor, etc. But we also have to integrate many data from other data sources, such as weather data, soil data, and satellite. But how do you integrate these data efficiently? They all come in different format, resolution, projection, and come in curves and sizes. Second, we learned that even though it is nice to work with a vineyard and saved over 1 million gallons of water, it only becomes truly impactful if this can be scaled up to regional, national, or even global scale. Then it will become a big deal. To understand the challenge of scale, here I show the daily data size of a few relevant data sets, which, as mentioned, can at different spatial and temporal resolution. For comparison, here is the Twitter data, which is not that much if you compare to the global European weather forecast model, which generates 8 terabytes of data per day. What does 8 terabytes mean, and what does it take to process it? In very simple terms, just to load 8 terabytes from a disk to the memory without other processing would take almost a full day. So we see that the geospatial data is often very complex. They are large in volume and then fast in velocity. Each data set takes experts weeks and months to learn, understand, acquire, curate, and finally be useful to that expert for analytics. This involves hundreds of pages of documentation and programming. The expert needs to be skilled in computer science, geospatial data analytics, and so on. And for other people, the data is just undiscoverable. It's unusable. So how can we solve this integration problem once and for all? The commonality of all these data sets is that they all have geospatial and temporal information associated with. We call them spatial temporal data. So we designed a master global grid, which has 26 levels of resolution, as I show here. And the resolution range from 0.8 meter to the whole globe. It uses simple latitude and longitude as coordinate, so it is a simple uniform projection system. The Z-order algorithm shown here transform the two-dimensional data into a one-dimensional array for easy process. The final key, design of the key for each data point, is a combination of spatial and temporal keys. In this way, we homogenized the various different data sets into a master database. So how do we scale after we have designed the integration approach? Here is the architecture of the pairs platform. It is composed of three main components. First is the data curation and ingestion engine. Experts will create the process, and the computer automates the process for scaling up. There are literally hundreds of projection systems used in the world. The computer engine will take care of data filtering, reformatting, and reprojection. Second is a core Hadoop HBase-based system built for large-scale data storage and processing. It is a highly scalable platform that new data nodes can be added as the database grows. This way, it is very easy to scale up from California to continent of USA and to the global scale. The Hadoop HBase system is a highly distributed system taking advantage of parallel processing and storage capabilities. Since the data are taken in the homogenized spatial and temporal format, they are intrinsically linked and correlated. This is a significant portion of spatial temporal data analytics task. So this is a perfect example of how to bring analytics to the data, not the other way around, because the data is too big to be moved. The third part is a user interface, which has both an API interface and an interactive web interface. And users can download their data of interest once they explore using the interactive interface. So we'll have separate demo videos in the web page. You can look at the demos on how this works. So we took care of both integration and the scaling challenges. Here is the current pairs hardware system. The ingestion engine interact with data source and the core cluster. The core cluster has over 4 terabytes of memory and half petabyte of data storage. The user interface is on IBM software server on the cloud. So here are the highlights of pairs platform compared with the current conventional approach. The conventional approach, each data set is kept at different place in different formats, projections, units, etc., resolutions. The petabytes of data are stored in billions of individual files and scenes. Analysts order things from each source. They have to do the whole through of downloading, assemble, resample, reprojection, align, etc. And the data has to move to application, and it does not scale. In comparison, pairs stores the large-scale pre-processed big data with pre-aligned layers. They have common format and projection with a global reference system, and the spatial and temporal drawing is just intrinsically built into it, so it's very easy. It has the intelligent query system and discovery tool that will be shown in the demo videos. And the analytics is done without moving the data. That drastically accelerates the query and discovery process. And we also have enabled the capability to put new layer of analytics back into pairs. So you derive it, get the data from pairs and do your model, and then you can put it back, and that will become available to other users. So to demonstrate the scalability of the platform, we have benchmarked the speed of queries as a function of the data size. Compared to the conventional approach, the same query speed for different data size, as you can see here. Pairs query gets faster as the size of the query increases. This is a result of the largely parallel and distributed Hadoop HBase system. Pairs scales much better than the conventional approach, as you can see here. So in addition to host publicly available datasets, we also develop our own one-of-a-kind analytics and offer them on pairs. Here is one example on solar energy forecast. This is based on a situation-dependent model blending, which was applied to derive improved accuracy in solar energy forecast. This analytics actually utilize live data feed of a sensor network of about 1,600 measurement sites to train multiple weather model and make cognitive discovery with 30% better accuracy than individual weather model forecast. So this data set is offered on pairs. And here's another example I mentioned. This is the energy balance model we talk about in the story of the winery project. Multiple data sets were required to calculate the evapotranspiration of a crop. As you can see, solar radiation, weather data, soil data, and sunlight parameters are all required in this case. So the forecast the model was first tried out in California, and then it was validated against 130 measurement stations across the area, and we derive excellent agreement. As you can see here, the green is the measurement and the blue is our forecast model. So from there, we scale up the model to the USA national first, and then to the global. So we have a global product of evapotranspiration. In addition, Pairs is strategically positioned to be complementary to other geospatial information system software, such as QGIS is an open source geospatial information system software, and also Esri. Here's one example showing we can retrieve elevation data from Pairs very easily, and then derive the aspect, that's a different parameter, by using QGIS software. So aspect is just showing what direction is the slope facing. So 0 for facing north, and it goes in degrees counterclockwise. So this process, it takes barely minutes in order to finish with the help of the Pairs platform. Usually it will take days because the elevation data comes in one huge file.